Hello and welcome to this video for Chemistry 20 in the stoichiometry unit. In this video, we're going to look at acid-base titrations. So what is a titration? A titration is essentially, a laboratory technique that we use. Now, the reason we're going to do this is because let's say we have the following scenario. I know that 10 milliliters of acetic acid is reacting with 0.202 moles per liter of sodium hydroxide. What is the concentration of the acetic acid? So if I write out this reaction, my acetic acid and sodium hydroxide, this will be a double replacement reaction, making water and sodium acetate. If I write down the information I have and what I want to find the concentration of the acetic acid. I know the volume of it reacting is 0.0100 liters. That's 10 milliliters converted into liters. I know the concentration of the sodium hydroxide, but in order to find the moles of at least one of them, I need to also know the volume, okay? And that's where a titration experiment comes in. It is an experiment that helps you determine the volume of an acid or a base that it takes to fully neutralize the opposite substance it's reacting with. So in this case, I'm neutralizing my acetic acid by adding sodium hydroxide. Okay, so we need to find this volume in order to find the moles of our given, making this our given, and therefore trying to find our wanted right there. Okay, so let's talk about this procedure. The titration is again a procedure used to find the volume of the substances that fully react with each other so that you can calculate the concentration of one of the unknown solutions. We call that the analyte, the unknown solution. This is also sometimes known as standardization because you are taking an unknown solution and standardizing it. Standardizing it means we're finding its concentration. We're reacting it against a standard solution of known concentration to find the concentration of an unknown solution. Strong acids and bases need to be standardized in this process over time because they slowly dilute themselves, reacting with the water that they're dissolved in. The solution this is the setup, I guess, and before I get into the setup, you have a long skinny tube here with increments on it called a burette, and you have a conical flask here called an I think I'm spelling this wrong, but you get the gist, an Erlenmeyer flask, okay? One of the solutions that goes into the burette is called the titrant. I also spelled burette wrong. And the solution that goes into the Erlenmeyer flask is called the sample, okay? The sample, so down here is your known volume sample, usually 10 milliliters, for example, that you pipette specifically 10 milliliters of your sample in there. There's also an indicator solution. Remember we talked about those indicator solutions in the acid-base unit. There is also an indicator solution that we're going to put in there that changes color when they fully react with each other, okay? So either your acid or your base is going to be the titrant. It depends on what your sample is. If your sample is an acid, your titrant will be a base. If your sample is a base, your titrant will be an acid, okay? Common indicators we use are things like methyl orange or bromothiamyl blue. We're actually also in this video going to talk about how to select which indicator you should use for your titration. But that indicator is there because when it turns color, you have reached the completion of the reaction, also known as the end point, okay? So a sudden change in color lets you know you have reached the end point, the completion of the reaction. Another way of saying this is it is when the moles of the acid equal the moles of the base. So my titrant has completely neutralized the sample. The equivalence point is the same point in the titration, but it is usually referred to the volume required of the titrant needed to reach the endpoint, okay? Now, when you do these experiments, you're actually going to do them multiple trials, at least 3 times, where your volumes of them are all the same essentially. By the same, we mean they have to be within 0.20 milliliters of each other. Okay, so they might not be exactly the same. If you can get exactly the same, that's perfect, but you're trying to get them at least within 0.20 milliliters of each other, all three of them, okay? And then we'll average them. Now, just a reminder here, when you're reading a burette, the numbers actually increase as you go down. 0 is at the top and 50 is at the bottom. And you need to make sure you're reading at eye level the bottom of the meniscus, and it is accurate to 2 decimal places. So centimeters cubed is the same as saying milliliters. So the correct value when I read the bottom of the meniscus, because that's 19.00, this is 19.1, 19.2, 19.3, and so on, okay? So the bottom of the meniscus is at 19.50 mils. Now, if you have the bottom of your meniscus in between 2 lines, because right now it's exactly sitting on this line here. But if it was in between 2 lines, then the second decimal place would be a 5. So for example, if it's in between 19.40 and 19.50, it would be 19.45. You estimate that second digit as either a 0, it's on the line, or a 5. Don't look at these here where they put 2s. We don't do that, either a 0 or 5. Okay? So let's get into an example and let's look at some sample data that you could see for a titration experiment. So a student is taking a 10 milliliter sample of hydrochloric acid, titrating it with, which means you're adding to it, the sodium hydroxide. Bromothymol blue is the indicator used, and it changes from yellow to blue at the endpoint. What is the concentration of HCl? So again, if I start with my, actually we'll get into sample data and then we'll get into writing the reaction. So again, the word HCl is titrated with sodium hydroxide, means the HCl is the sample and the burette, the titrant, is the sodium hydroxide. You're adding the sodium hydroxide to the HCl. Now that's important because you need to know what's in the flask and what's in the burette. Sample data is always going to give you all of the information about the burette, okay? The solution, the titrant in the burette. You are going to be given an initial volume, or you're going to do an experiment, and in trial, these are the different trials. In trial 1, you're going to fill it up close to the top. It doesn't have to be exactly at the top. And then you're going to let the solution drain until a color change happens. As soon as that color change happens, you stop the burette from emptying and record what the new or final volume is. Then you subtract these volumes and it tells you what volume you actually added in that trial, okay? So 11.3, I don't really need a calculator for this, but anyway, would be 11.10, and these are milliliters. Okay, now when you're using a burette, there's a nozzle on it that controls, again, the opening and closing to allow solution to drain out, but you can also control the speed at which it comes out. You want, like a good titration experiment, to have a 1-drop difference of color change. So you want it to be really slow when you get close to the end point. But if you go really slow the whole time, it's going to take way too long. So our first trial is usually called an overshoot. You let the solution drain out really fast, and then just with reaction time, by the time you stop, you've way added too much, okay? But it gives you an approximate what volume is required. So in the next trial, notice how you don't refill your burette. Wherever you left off in trial 1 is your new initial volume for trial 2, okay? So you don't need to refill it. You start where you left off, and then again, you can let it run really fast till you add maybe 8 or 9 milliliters, because we know the endpoint is 11 is over, but close. You let it run fast for 8 or 9 milliliters, then slow it down until you, like I said, get that 1 drop that changes it. It's going to start yellow because in hydrochloric acid as our sample, it's going to be yellow. And then it's turning a light blue-green when we reach the endpoint. You want that slight tinge change of color to let you know that you've reached the endpoint. So you turn off the burette After that color change happens, you need the indicator color change to know when the endpoint is reached. Subtract these values and find out that in a more accurate trial, we got 10.95 milliliters for the volume of sodium hydroxide required to neutralize the 10 milliliters of hydrochloric acid in the flask. Now, these two volumes actually look okay. They are within 0.15 of each other. And remember, the accuracy we're looking for is for them to be within 0.20 milliliters. So this is within the limit, but I need at least 3 trials that don't have to be subsequent, but at least 3 that are all of them within 0.2. So we then go to trial 3. At trial 3, again, I start where I left off from trial 2. I let the solution drain until I reach that slight color change. Then I subtract the final volume from the initial volume and find that I got even more accuracy. Usually when the volume gets less, you're getting more and more accurate, closer and closer to the endpoint. Now these trials 1 and 3 are not within 0.2. So that means either this one was too low or this one was too much. Usually your overshoot is too much. Okay, when you get smaller and smaller volumes, you're usually getting closer and closer to an accurate endpoint. All right, so now we need another trial that hopefully is also within 0.2. These are within 0.2. These will need to be within 0.2, and all the first and the third have to be within 0.2, or the second and the fourth in this case. Okay, so 44.05 is where I left off or shut off my valve and in trial 4. I'm subtracting it from where I started in trial 4, which was 33.05, and I get a volume of 11.00. So all 3 trials, trial 2, 3, and 4, are in fact within 0.20 of each other. 2 and 3 are, 3 and 4 are, and 2 and 4 are. So our overshoot trial does not get used in our average volume. We only average the 3 within 0.2. If you're doing an experiment, a titration experiment, you're going to repeat trials until you get those 3 that are within 0.2. Again, they don't have to be subsequent trials, okay? But you need 3 that are within 0.2, and then you're done the experiment, okay? So what I'm going to do now is average these volumes. So I had 10.95, I had 10.80, and I had 11.00. I add them together and then divide by 3. 10.95 plus 10.8 plus 11 divided by 3 is 10.92. Remember again from the charts, this is my volume in milliliters. Now I can go back and complete the question. So remember the question was saying that we are using a volume of 10 milliliters of the hydrochloric acid. I want to find the concentration of the hydrochloric acid. I was given the concentration of the sodium hydroxide, and I now know the volume of sodium hydroxide that it takes for it to fully react with the 10 milliliters of the hydrochloric acid. Converting this into liters would be 0.01092 liters. Remember, you always want to have everything in liters. Okay? So next, oh, there was a little space there for me to put that. Now, this is a solution stoichiometric calculation. Okay? I am going to find the moles of my given with C times V. So 0.685 moles per liter times a volume of 0.01092 liters. So our liters cancel, and we will be left with moles. 0.685 times 0.01092. We get 0.00748, so on, as our moles given. Now we use them to find the moles of our wanted. That value times wanted over given, which would just, in this case, be 1 over 1. In front of my wanted, there's a 1. In front of my given, there's a 1. So the moles of my wanted are the same value, 0.00748. Remember, though, to use the unrounded answer from one step to the next. Now I am looking for concentration, so I need to take the moles of my hydrochloric acid and divide by the volume of my hydrochloric acid. Okay? And that will give me moles per liter for my answer. So I divide by 0.0100, you don't really need the zeros after, but the answer we get now, the concentration of my HCl is 0.748 moles per liter. So that's the overall purpose, again, of a titration experiment, to find the concentration of one of the solutions, the acid or the base. The titration data lets you know what volume it takes for them to fully react. Okay? Now, the other thing we're going to look at is if we were to graph a titration experiment, what would it look like? Okay? So the titration experiment is going to be a plot, it's called a titration curve, a plot of pH versus the volume of titrant added. Okay? The titration curve is not a straight line. It actually makes sort of an S shape. I don't really want to call it an S shape, but it kind of looks like that. And you'll see what I mean when I look at an example. Whenever you have a strong monoprotic acid with a strong monoprotic base, your end point or equivalence point is always going to be at a pH of 7. Now, there's two curves that you need to know. You're going to either have an acid being titrated with a base or a base being titrated with an acid. So what it's showing is the pH of the sample. So the first point on the curve will be if it's an acid, really low, if it's a base, really high. There's a very gradual change at first during a titration called the buffer region. And then as you get close to the endpoint, the pH changes very rapidly. It spikes up or down really quickly. Okay? If you over-titrate your sample, it is going to be asymptotic to the pH of the titrant. So let's look at these curves. So this is a strong acid, like HCl, being titrated with a strong base. That means your strong acid is the sample, and your titrant, what you're adding to it, is the base. Okay? The curve is going to have the volume of titrant added on the bottom, the pH on the side. You don't need to label all the pHs, but you want at least 0, 7, and 14. And so the pH curve is showing, again, what's happening to the sample. So my sample is an acid, which means my pH is starting around 0. Okay? Then this is what the curve is going to look like. Okay? So what happened was at first the pH was relatively stable because I have a huge amount of acid in my flask. I'm only adding a couple of drops of the base, so it neutralizes and therefore stays relatively flat. This again is called the buffer region. The initial flat region is the buffer region. Okay? Then when you get close to the endpoint, the pH spikes up really quickly. That's why I said you want just one drop to make a difference of reaching the endpoint. The endpoint is the middle of the spike up. Right there is your endpoint. Okay? That would be, again, at a pH of 7 when you have a strong acid being titrated with a strong base. This is where you would end the experiment at the endpoint. But we also show the over-titration. So if you add too much base, what would happen? The pH of the base would take over, and it would be the pH of the strong base. Okay? So that is a strong acid titrated with a strong base. The other curve you need to know is a strong base, this time as your sample, being titrated with a strong acid as your titrant. Okay? So this time, similar setup, But my pH is going to start high because I have a base as my sample, and it's going to go down in a similar fashion. It goes down very gradually at first, and then it spikes down really quickly when you are close to the end point. So again, the middle of that spike is your end point. This initial flat region at the higher end now is the buffer region. And then this point after the end point is the over titration. So if you're asked to draw and label a pH curve, make sure you have a title. You have your axes labeled. You're labeling the buffer region, the end point, and the over titration. And this is what it means by it's S-shaped. It's not really S-shaped. Don't make an S, because that means your volume's going backwards. Your volume can't go backwards, okay? So it's not really an S, but it's also not just a straight curve down, okay? It's flat, spikes down, and then flat again, all right? The last thing we have to look at is choosing an indicator for your titration. The pH of the endpoint needs to fall within the range that the indicator turns color. Now again, when you have a strong acid with a strong base, monoprotic for both of them, that endpoint pH will be 7. But in the experiment that my students actually do, our endpoint is I think 4. So we use methyl orange as our indicator because 4 is where that methyl orange is going to turn color. Pretend you have another question here. You're completing a titration lab and the endpoint is occurring at 9.0. What indicator should you use? So you're looking where 9.0 is within the range that it changes, and therefore your answer would be phenolphthalein. Okay? And that's it for titrations and the end of the Stoich units. In most classes, the Stoich is the final unit, so the end of Chem 20. Thank you very much for watching this video.